Welcome to a quick review of Chapter 6 from Statistics, Discrete Probability Distribution, starring the binomial distribution. Some quick definitions. A random variable, usually denoted by capital X, is a numerical measure of the outcome of a probability experiment. And whatever its value is determined by chance. If you're dealing with heads and tails, you call them zeros and ones. You could do temperature, tossing dice, whatever. Discrete random variables are the variables which are finite or countable, or think of them as if you had a number line, there would be spaces between the points of possible values. As opposed to those are continuous random variables. Those would be the variables that have infinitely many values, or think of it as being able to be plotted in an uninterrupted fashion. And technically, our continuous random variables are limited by the human's ability to measure them. But if you think you have a stopwatch and it goes to the hundredths of a second, or even more precise than that, you could basically say, even though I cannot perfectly measure it, it is a continuous random variable. Probability distribution are the possible values of your random variable x and the probabilities associated with each value. And this can be shown in a table, a graph, or a formula. Rules of discrete probability distribution. Every individual probability still has to be between 0 and 1 inclusive. That's just how probability works. And when you have probability distribution, all your probabilities together must sum to 1. You must be showing all possible events. A probability histogram is much like the histograms you've seen before, but now your vertical axis will be the probability. In this example, pretend those are percents. I did not convert them to decimals, but your values, possible values, in this case I have a range of values across the x-axis for temperature, and the probability of that day's high temperature falling in that range is given by the percent going across the vertical axis. To calculate the mean of a discrete random variable, that would be mu sub x, x because capital X is our random variable. The mu of random variable x is going to be the sum of each possible value of x, shown by little x, multiplied by the probability for that value. So if there's a 0.03 chance of getting a 5, you do 5 times 0.03. And then there's a 0.07 chance of getting a 6, it'd be 6 times 0.07. Add all those up, you will get your mean, mu sub x. Now, x bar is what you've gotten through your experiments, and that would be just adding up all the values of your n observations and then dividing by n. Now, as your n, that's your number of trials, experiment, whatever, as that number gets bigger and approaches infinity, your x bar should be approaching the actual mu sub x value. Okay, variance and standard deviation can also be calculated for discrete random variables. Variance is sigma squared, and we're talking about random variable x, so sigma squared of x, and that's calculated by, for each possible value, take x minus mu sub x, square it, and multiply by the probability of having gotten that x. That can be simplified to the sum of, and then you do x squared times probability of x, take the sum of all those values, and at the end subtract mu squared. And if you want standard deviation, you just take the square root of your variance. All right, moving on to binomial probability distribution. There are criteria. First of all, there's a fixed number of trials. We're not going on to infinity. The trials are independent from each other. Just because you get a heads once doesn't make you more or less likely to get heads the next time. For each trial, there are exactly 2 possible outcomes. They are mutually exclusive, and you think of it as success or failure. If it's heads and tails, pick one to be success, pick one to be failure. All right, and the probability of success is the same for each trial. To go over the notation we use, the number of fixed trials when we're doing a problem, that would be n. The probability of success in a given problem would be p, and then the probability of failure is the opposite or the complement of that, which would be 1 minus p, and we're going to use capital X to be the number of successes in n trials. So the probability of 5 would be the probability that we have 5 successes in however many trials n is, whether that's 10 trials or 100 trials or whatever. All right, binomial probability distribution has a formula, and we're going to start with a combination. Remember, combination order does not matter as opposed to permutation where it does. So that is the formula that has 1 factorial in the numerator of the fraction and 2 factorials in the denominator. That's what we want for combination. So we have NCX, that's the combination of choosing X things out of N options. So that's N factorial on the top. On the bottom, we have X factorial and N minus X factorial. We're going to take that, multiply it by P, our probability, to the xth power. And we're also going to multiply it by 1 minus P, the probability of failure, or the probability of the complement, the other option. And that is being raised to the N minus X power. And this formula holds for any X from 0 up to N. Let's look at an example of how that works. What's the probability of getting 5 heads in 7 tosses? So the number of tosses is 7. The successes we want, our X is going to be 5. So N is 7, X is 5. We're going to assume this is a fair coin, so the probability of a success is 1/2. And in this case, the probability of failure, or the probability of tails, is also 1/2. So what if we got 5 heads in a row and then 2 tails? Well, the probability of getting a head on the first toss is 1/2. Next toss is 1/2, 1/2, 1/2, 1/2. And the probability of getting tails on the last 2 tosses, also 1/2 for each of those tosses, which is a total of 1/128. However, the order doesn't matter. We just need 5 heads somewhere in those 7 tosses. So you could arrange it however you want so that out of 7 tosses, there's 5 heads thrown in there and 2 tails. So to do that, that means we can arrange those 5 heads however we want in those seven tosses. So we're going to have 7 factorial over 5 factorial, 2 factorial. That's our combination. So there's 21 ways that we can actually get 5 heads and 2 tails. So if you take the 21 ways you can have 5 heads and 2 tails, and the 1 in 128 possibility that you could get 5 heads followed by 2 tails in that specific order, then the way you could get 5 heads and 2 tails in any order would be 21 over 128. Let's do another example where the probability of success and failure are different probabilities. So in other words, our probability is not exactly 1/2. So let's say the probability of rolling 2 6s out of 5 rolls. Okay, so the probability of rolling 6 is 1 in 6. That has to happen twice. The probability of rolling anything but 6, which I'm going to go with a C for complement, so it's basically not 6, that's 5 in 6, because it could be 1, 2, 3, 4, or 5. And there's going to be 3 of those rolls. So it's 1 6 times 1 6 times 5 6 times 5 6 times 5 6, which is 5 to the 3rd power over 6 to the 5th power. But that only tells us about that specific order. And remember, order doesn't matter. We just need 2 6s somewhere in those 5 rolls. So we're going to multiply by the number of combinations we can make. So that is out of 5 things, we're going to choose 2. 5 factorial over 2 factorial, 3 factorial, and that works out to be 10. So there's 10 ways that we can arrange those 2 6s in a total of 5 rolls. So our final probability, and this is where we go back to the actual formula, is 10 times 1/6 to the 2nd power times 5/6 to the 3rd power. And if you work that out, it turns out to be about 1.6%. Finally, we can calculate the mean or expected value, that's the same thing, and also the standard deviation for binomial random variables. Mu, your mean, mu sub x, is just n, the number of trials, times p, the probability that you'll have a success in each trial. Nice and easy. Standard deviation is not so simple, but it's not so big you can't memorize it. Okay, standard deviation of x is the square root of n times p times 1 minus p. So you take the number times the probability of success times the probability of failure, and then that would be your variance. Take the square root of that whole thing, you get your standard deviation. And finally, the binomial distribution does approximate the bell curve. If you take that NP1 minus P, which was just under that square root sign we were talking about for standard deviation, the rule of thumb is that if that NP1 minus P is greater than or equal to 10, your distribution will be approximately bell-shaped. All right, that's it. Good luck with Chapter 6.